Yo, what up, YouTubers? Welcome back to Structure Free Learning. And in this video, we're going to do some mechanics and materials and look at a lap shear connection design example. And what we're trying to do in this lap shear connection is transfer essentially 10 kips from one end to the other end through a lap connection, which is two plates on top of each other connected by bolts. And in this case, I've got 4 bolts here, and you can see if I looked at the side view of the connection, I'll see here you see 2 of the bolts here. What's given to us in the information is that we got the plates are made of grade 36 steel with material properties shown, and then in the bolts, we're going to choose A325 bolts. And what we want to do is determine what area of plate we need, considering a factor of safety of 2 from the yielding of the steel, and we also want to select a bolt diameter with the safety factor of 3 from bolt shear fracture. The first thing I'm going to do is design the area of the plate. In order to do that, I want to start off by looking at the basic design relationship, and the limit state or the failure mode that I'm considering for this plate is yielding on the gross area. So here, this line right here, or a cut through this plate, represents yielding on the gross area, or where I might get failure. And this failure is through normal stress. The basic design relationship I want to start off with is the basic design relationship for normal stress on the plate, which means that I would have sigma applied is less than or equal to sigma allow. The sigma allow is the material property I'm considering, which is the yield, the normal stress yield of my plate, divided by a safety factor, which we're told is going to be 36 KSI divided by a safety factor of 2. And that means that my allowable stress is 18 KSI. For the applied stress side, I want to substitute the constitutive relationship for normal stress, which in this case for axial loading is simply the internally applied force, I call that N applied, divided by the area or the cross-sectional area that I need to satisfy this basic design relationship and make this less than or equal to 18 KSI. And now what I'm going to do, from statics, I know that this N applied, the normal force applied on this green face here, is 10 kips. So this is 10 kips, and I can solve for the area that I need, or the cross-sectional area that I need for my plate in order to satisfy the basic design relationship. So in this case, this would become that the area required is greater than or equal to 10 kips divided by 18 KSI, 0.56 inches squared. And that means that whatever cross-sectional area that I choose, I have to have an area that's greater than or equal to 0.56 inches squared. So here I've drawn for you what the connection looks like in 3D. And what this A required means is that I have to choose this cross-sectional area here for both of the plates, really. But I have to choose this cross-sectional area so that it's greater than or equal to 0.56 inches squared in order to satisfy this basic design relationship. So that means I've got to choose a thickness and a width, some T and B, to satisfy this basic design relationship. And so if this plate is manufactured by thicknesses, so there's preset thicknesses, and I can cut it to any reasonable width. If I had a 1/4 inch thick plate, all I gotta do is substitute. Let's see, the area of this plate would be B times T, and I want this to be greater than or equal to 0.56 inches squared. T is a 1/4 inch. Then I can solve for B, and B has to be greater than or equal to 2.24 inches. I would have this 2.24 inches, and then I can go and I can also check it for, like, let's say a 1/2 inch thick plate and a 3/4 inch thick plate. And that would tell me, if I just go ahead and I repeat that same process, I would need a width of 1.12 inches for a 1/2 inch plate and 0.747 inches. So looking at my design results, if you will, I can, as an engineer, I can choose what's the most efficient, or whatever is going to fit my application. And here in this case, if I chose a 1/4 inch plate, I'm probably going to specify a plate that is a 1/4 inch by 2.25 inches. And if I choose a 1/2 inch thick plate, I would want to specify a 1/2 inch by 1.25 inch plate. And if I choose this, then I might choose a square rod here. This would be a plate that's 3/4 inch by 3/4 inch. And so these would be my designs. One of these three will be the design for my plate to satisfy this basic design relationship with respect to yielding of the gross area. The next thing I want to do is check the bolt, or select or design the bolt diameter. And so in order for me to do that, I need to recognize that when I apply this loading here, this 10 kip loading, and I want to transfer it across to the other plate, it transfers through the bolts by shear. And so if I draw, let's say a cutout, this cutout here in 3D, this is what it might look like. So here's what the bottom half plate, or the bottom plate, might look like here. I have the 10 kip load, and then this would be kind of a slice through each bolt diameter, and across each bolt there would be an internal shear force that I will say is equal. Everyone has an equal share in resisting this 10 kip load. And so the shear force inside each bolt would be, by equilibrium, sum of the forces in this direction equal to 0. I'd have minus 10 kips plus 4 times V equal to 0. And each internal shear force would be 2.5 kips. Now, in order to select the bolt diameter, I have to start at the basic design relationship, BDR, for shear inside the bolt. And that would mean that I want tau applied inside the bolt to be less than or equal to whatever shear I allow inside the bolt. And for here, the limit state is shear fracture of the bolt. And this tau allow is going to be tau ultimate, or tau fracture, tau ultimate, divided by the factor of safety. And so what I'm going to be allowing is 54 KSI divided by 3, which is 18 KSI in each bolt. That's the maximum stress I'm going to allow in the bolts. Constitutive relationship, or the relationship that turns internal shear into a average shear stress, is going to be V applied divided by the cross-sectional area of the bolt. And I want that to be less than or equal to 18 KSI. I know that within one bolt, this V applied is 2.5 kips. And so that means I would like the area of my bolt to be greater than or equal to 2.5 divided by 18, which makes this 0.139 inches squared. And in order to turn this into a diameter selection, I just have to substitute the area of a bolt, the cross-section area of a bolt. I'll just say it's pi over 4 times the diameter of the bolt squared is greater than or equal to 0.139 inches squared. And if I solve for dB, I need the diameter of my bolt to be greater than or equal to 0.42 inches. And because I can't choose a 0.42 inch diameter bolt, they probably don't make them that big, right, or that size. You know, I'm going to say for my design, I'll say choose, I'll put this in purple, choose dB equal to ½ inch. So I'm going to choose ½ inch diameter bolts made of this A325 steel material. Now, this also has ramifications which are not necessarily stress based on my plate dimension as well, because here, if I choose a ½ inch diameter bolt, I need to have enough space on my plate. If I go back over here, if I choose a ½ inch diameter bolt, I got to make sure I have enough space or enough width here to accommodate, you know, a half inch. That's already 1 inch, and then I have some space requirements here so that I can fit my tools to tighten any bolts and nuts, and just so that, you know, aren't any other failure modes that can occur. But that's more with if you're designing steel structures or other kind of metal structures, and there's minimum edge distances and spacing requirements. Anyways, hopefully that this was a little helpful and insightful in terms of designing a simple lap shear connection. All right, if you have any questions, let me know. Take it easy.